I was able to predict the radius of the proton precisely in 2012, 4% smaller than the proton that was being measured at the time. 4% in quantum physics is huge, you know?
Yes.
The force that holds the protons together is actually the gravitational force of little black holes. We've accounted for all the material of the milk, but ignored the coffee. Of course, we're missing 80% of mass, right? There's been some intent to make this kind of knowledge difficult to obtain. It has affected me deeply. It's been super difficult.
Welcome, Nassim.
Thank you. It's so good to be on your show.
I've watched you over the years, and probably the best part of this job is getting to meet people like you and pick your brain. You're so knowledgeable, over 30 years of experience. So my first question is, in your recent 2023 paper, The Origin of Mass and the Nature of Gravity, you demonstrate that mass emerges from quantum vacuum fluctuations rather than being an inherent property. Can you explain in simple terms, I guess, or as simple as you can for my audience initially, and then we can get into more technicality, how this fundamentally changes our understanding of reality?
Yeah, I mean, it's the thing is that mass is thought to have emerged from the Big Bang in this kind of miracle way, and we built some various mechanism in the standard model to try to address the source of mass. I mean, it's inside Einstein equations, for gravity. So you have a mass and it's curving space-time and all this, but you're assuming the mass, you're putting it in. It doesn't tell you where the mass come from. And actually Einstein tried with Nathan Rosen to make more fundamental theory about mass, and we'll discuss that later on. But as well, in quantum mechanics, it's the particle mass in later years have been thought to have come out of a field called the Higgs field, and that gives the mass to subatomic particles. But when you apply this mechanism to the proton, which is the nuclei of the atom, which has most of the mass, like the mass of the universe is taught in terms of the proton mass. And so when you use those mechanisms, you only get 1% the mass, the proton, 1 to 5%, depending how many free parameters you throw in there. And, and the rest is thought to come from gluon fields that are not analytical solution. They're not closed solutions. So basically you can only run supercomputers for years, costing millions, if not billions of dollars to get an approximate answer at the end so it's definitely not fundamental. It's not first principle. And in this paper I published, I kind of extended what I had found in 2012, showing that there's a field called zero-point energy that was discovered by Max Planck at the beginning of quantum mechanics, like the very, very beginning. And basically, quantum mechanics describes an oscillator in a field in quantum field theory. But in the case of Max Planck, it was just an oscillator. And it's an equation that says how much energy is emitted by the oscillator when it's heating up, when it's absorbing energy and emitting energy. And the equation is right for all of the measurements we do. It does a really good job on everything. And then when you set the equation so that the temperature is at 0 Kelvin, where the oscillator, the little atom or the little particle, whatever, should stop oscillating. There should be no thermal agitation. There should be nothing happening. The equation actually says that there's an infinite amount of energy there that's
Okay.
left. It still jiggles.
So that's really the idea of 0 point energy then, is that at zero
Yeah,
Kelvin, there is still an amazing amount of energy.
exactly.
If you watch my videos, you know I'm always complaining about censorship and digital control. And I don't think that's paranoia, actually. I think that is reality. That's why I use a virtual private network. And I'm proud to say this video is sponsored by Private Internet Access. With PIA, my connection is encrypted. So no one, not your ISP, not big tech, can see what you're doing online. PIA also lets me access the full internet, not just what's allowed in Portugal or the US, for instance. So if you need to use a streaming site or log in from your home IP while you're traveling, it's no problem. There's 91 countries and you can get instant access. PIA covers unlimited devices, so I can use it on my phone and my laptop, no worries. If you use my link, piavpn.com/Lehto files, you get 83% off. That's just $2.03 a month, plus 4 extra months of free. Link is in the description. Thank you so much for supporting Lehto files and protecting yourself. Now, let's get back to the video.
And, that was difficult to deal with when it was discovered and all this, and people debated if it was real or not, and so on. And then eventually it was measured by the Casimir effect, and the dynamical Casimir effect as well, and so on. And so we know it's there. Actually, it's present in a lot of quantum mechanics, is required. It's an electromagnetic fluctuation of the structure of space itself at the very fine scale of this, like the Planck scale. And basically, I show in this paper that so in general, what they did is that they zeroed it out. They made it like, okay, we're going to assume that all the waveforms, they're called modes, all the modes of oscillation of this field of electromagnetic fluctuation that's occurring at the very fine scale, we're just going to assume it all cancels out, and we'll put it at zero, call it the ground state, and build physics from there. And this paper just shows that actually when you treat it rigorously, it's called the correlation function equations. They're equations that describe how many waves are going to be constructive and how many waves are going to be destructive. Inside the cavity of a proton, you get exactly the mass of the proton, showing that mass actually emerged from this fundamental field. And that might sound kind of like, so what, to layman, but I assure you it's a big change in physics. But as well, it says something profound. It says that like energy and mass, like reality, emerge from a fundamental field that we didn't really assign the proper mechanism to early on. And yeah, it got a bad rap throughout the years because many inventors, were saying they were going to extract energy from 0 point energy. There was a pretty big campaign of disinformation about 0 point energy, but it is a fundamental principle of quantum mechanics, and it is at the foundation, and you can't just remove it. In fact, if you remove it, which like is done in many cases in the equations, the little oscillator I was discussing, which is like the particles that make up our reality, would stop oscillating. The equations become commutative instead of being non-commutative. That means that like there's no more source of energy for the little oscillator to continue to oscillate. So as soon as the Big Bang happened, within a few billionths of a second, like all oscillators should have lost all their energy, and reality wouldn't be what it is today. So the paper argues that actually well, argues mathematically, shows rigorously that actually you can't just put that energy to zero and then call it a day. You actually have to deal with it. And when you consider the energy inside the proton, like I was saying, you get the right mass from all the waveforms that are producing energy, that are constructive. And if you consider how much energy is available at the scale of the Planck scale, which is a very, very fine scale, you do get the right answer, which is the Planck density. So it's consistent, right?
Well, I had a question about oscillators because in my mind, an oscillator, a simple oscillator, is like a spring, right? Where it's just a two-dimensional back and forth oscillator. But in our three-dimensional world, it seems that everything is related to spin, essentially. You have the toroidal flow, right? It will spin one way, and then you have the basically horizontal spin as well. So basically, spin in two directions is how I kind of think of the three-dimensional universe. So is that an oscillator? Is an oscillator a spinning
Yeah.
entity, an orbit?
Yeah. I mean, this is one of the issues we take on right away in the paper at the beginning. The tendency is in universities when they teach to students about oscillators is to describe what you said is like a spring with a weight on it, and it's
Yep.
like basically a one-dimensional motion, right, going up, back, up and down. But that is the wrong visuals. And it's not a good analogy. I don't think they should use that. And that's really kind of important for people to understand. And that's why we start the paper like defining the oscillator. Certainly, Max Planck probably wasn't thinking of a spring and a weight when he was trying to describe particles as an oscillator. Yeah. And so, an orbiting orb spinning, a little spherical spinning object, is an oscillator as well. And the mathematics are consistent across. You can do a spring with a weight or a little spinning orb. The difference is that in one case you probably have the wrong picture of what the universe is making, and in the other case you have something probably much closer to what the universe is making, which probably involves like deeper level of toroidal structures, as well as you were describing with like fluid dynamics of a toroid, which has poloidal movement and toroidal movement. And we address that in the paper very lightly in the paper you just described. But we have a paper in peer review right now that it goes much more into the details of the flow of this. I call it a Planck plasma, like this field that organizes in region and makes up the material world we see.
So, and what has always been miraculous to me is in physics, rules such as the right hand rule, right? Where you can determine flow of force or torque, right? Can you describe why is the right hand rule? Can you describe it, I guess, briefly, and then can you explain why that is in our universe?
Well, that's a good point. Because there is, so the right hand rule is how you can identify the orientation of various field, usually the electric field relative to the electromagnetic, the magnetic field,
Yes.
in an element, in a chart, and you can definitely get a sense of what's happening by utilizing this relationship, which is a geometric relationship. And it really is saying something about the nature of magnetic fields and electric fields that's commonly kind of overlooked. And because it really is saying something about how fields are not stagnant, that it might look like a static, stagnant thing to us, but it is the dynamics of spin at scales that we're not directly measuring. I'll give you an example. There's an experiment that's called the Einstein de Haas experiment. And it's an experiment where you put a metal rod, or a metal tube inside a coil, like a solenoid. And when you put it in the middle, all the vector of forces in the coil should cancel out. And there should be no effect on the metal rod. There should be no movement of the metal rod. And what happens is that the metal rod starts spinning. Okay, it has a torque, and the only way you can explain that is because, and this is the way it's explained, although this experiment still gets ignored quite a bit, is that all the electrons in the metal are lining up, and all of their angular momentum together are producing a bulk angular momentum is conserved in the rod and making the rod spin. And the reason I'm talking about this experiment is because it really lands that there is real angular momentum at the quantum level, that it's really stuff spinning. And because in quantum mechanics, we've kind of got away from the reality of spin, although we use it in all kinds of ways in the equations. We say that the spin of particles is some kind of esoteric thing that is like spin 1/2 and so on, and that it's not really spinning. And that's just because I think we didn't truly understand the dynamics of the flow. It really is like circulation of a fluid. And so it's more complex than just like a simple object spinning. That's true. That's not quite that. But there is a fundamental dynamic of flow of this fluid dynamics. And that's why my equations give the right answers.
I know that Maxwell, in his initial equations, he started with quaternion mathematics, and then he simplified it. And I've Dr. Unzucker, he's a physicist from Germany. I don't know if you know of him, but I interviewed him as well. And that's his suspicion, is that spin, we may be missing some of the finer points when we simplified Maxwell's equations. Do you think quaternion mathematics is a way to describe it, or do you think you've hit on the correct answer?
No, I mean, quaternions are really useful, and I think there is a lot to be gained to like understand the quaternion formalism of Maxwell's equations, which Heaviside linearized and reduced from some 20 equations, I believe, to 4. But there's a really important part to understanding what is called the A vector, the potential vector in Maxwell's equation that Dirac and others mention, is really is describing a velocity, and it's ignored generally because in general, this portion, I'm just gonna simplify it because it can get complex, but just this portion of the predictions of Maxwell's equations were taught to not have a physical reality. Like basically, the A potential vector was taught to be like, it's just mathematics. It doesn't have physical meaning. Now experiments are showing that it does. It really has a physical meaning, and it is a velocity. And Paul Dirac, which if your viewers don't know, was one of the greatest physicists. He wrote very important equation, quantum field theory, and so on. He wrote papers saying, we should pay attention to this. It's telling us something about some kind of ether, fluid dynamics, some kind of flow, some kind of circulation is happening, and that is really an important part that's being overlooked, because what it means is that if there's a flow, that means there might be a way to tap into that flow. And so you got to wonder why there's been such a huge, let's just say, tendency for anything that has to do with a fundamental field that's flowing at the atomic level, that is making the electromagnetic field and the gravitational field. In our equation, in our paper, we show that actually it's curving space-time. This is actually how atoms get made. They're like little black holes. I know that might be shocking to people, but actually we can discuss that more. But basically, there's been a lot of interest in making this fundamental field disappear throughout the years. And although even Einstein, after writing general relativity, some 10 years later said, general relativity is basically inconsistent if it doesn't have an ether. What is curving space-time? Like, what is this thing, space-time? It must have some physicality. It's producing force, and so all this, I think, that's what Unziker was like pointing towards, and I think he's quite correct about that.
So from what I understand, Nassim, is your basic understanding of the proton, or the model I have in my brain, is that there is a quantum field, if you will. I think in the past it was called an ether, some sort of medium where you can have flow of what we would call energy, and the proton would be constructive and destructive interference, some sort of geometry. And you mentioned the black hole, which would be basically light or energy cannot escape from that little geometry of space, that three-dimensional area.
Right. Well, that's the thing, is that Max Planck discovered the zero-point energy, right? So ether is an earlier theory, and it had all kinds of quirks that we don't need to bring forward. But from the discovery of Max Planck, which is consistent and measured, there is an electromagnetic. We know there's an electromagnetic field that's oscillating with very high energy levels at the quantum scale, at the Planck scale of the quantum scale, so like billions of times smaller than an atom. And people have a hard time with this because they say, well, why can't I feel it? And my answer is often, well, you're calling it matter. You're calling it your body. But why can't I see this energy? Well, we see it in laboratories in certain ways, but as well, and we see it jiggling the electron, right? As well, we measure that, and but what's important there is that to understand that, like, if you have an energy at the base of creation, at the base of the material world that's oscillating, that energy should curve space-time. It should produce gravitational effect. It should not just be sitting there doing nothing, right? It would make forces. It would make things happen. And in general, it's been ignored that that should be happening. John Archibald Wheeler looked at it like head on and said, well, actually, maybe it is curving space-time and it's making little particles. The fluctuation of that field is making little particles that are at the Planck scale, and he called it quantum foam, right? Because he calculated that, like, the energy of that field should curve space-time and so much that it kind of like pinch itself into a little bubble. And, he called it the quantum foam. And then I came along and I said, well, maybe it's pinching at different scales, right? So I looked at the little foam bubbles and I said, okay, well, if there's a whole bunch of these, and I'm talking a whole bunch because, there's a huge scale difference between the Planck scale and the proton scale. If I grew a little Planck scale bubble to the size of a grain of sand, then the proton would have a diameter from here to Alpha Centauri, like 40 trillion kilometers, right? So, yeah. So imagine the amount of grain of sand you can put inside like a bubble that big. So I realized that actually at the proton scale, the pinch of space-time for the proton energy would be exactly what we measure as the strong force. Like the force that holds the protons together, which is like gravity, which is called a strong force, is actually the gravitational force of little black holes that are pinching space-time in that region because there's enough energy in the 0 point vortex that it has created at that scale to make that force. And so if it was like a good approximation or like within orders of magnitude of each other, I'd be like, but it's exact. And what's really crazy is that it's something that Einstein had found, meaning Einstein tried to make particles out of mini wormhole black holes with Rosen. It's a famous paper, and he wrote in 1935 where he tried to make, in his equation, he didn't have a source for mass. He was wanting to figure out where is mass coming from. Yep. So with Rosen, they tried to use this general relativity equation to make particles out of them. And he ended up making little wormholes. This is where wormholes, yeah. This is where wormholes physics come from, actually.
Okay.
And the mouth of these little wormholes would be the particles in his equations, and little black holes at the mouth of the little wormholes. But when it was calculated for a proton, it made a proton size billions of times smaller than the Planck.
Yeah.
So it didn't work. It gave the proton size of 10 to the minus 52 meters. It was so small, it cannot be a proton, right?
Yeah, exactly.
And what nobody noticed is that, and they couldn't have noticed it, Einstein and Rosen, because the strong force was not measured yet at that time. And, Yukawa had just started publishing papers, and like there was but nobody went back to this in the future when we had measured the strong force. But what they had found is exactly the ratio between the gravitational force and the strong force. That ratio, the radius they got for the little black hole proton was like exactly the ratio of the energy of the strong force. So if Einstein would have known this, I'm sure he would have solved it. You know, if Einstein would have known this, I'm sure he would have seen this. He would have solved it. But basically, what I did is said, well, instead of looking for the radius of the black hole, keep the radius of the proton, and then figure out how much energy do I have to put in the proton for it to become a black hole. And the energy you have to put in is exactly the energy you need to produce the strong force.
Wow.
You see, so the energy, we measure the black hole energy, we call it the strong force. You see, I just got to put a little caveat on that. I don't want to do a monologue. I'm sorry. But,
No.
you know, it's exciting because it's like, and people have a hard time with this, but it's like when we measure black hole in the universe, right? Like one of the big ones, when we measure them, how do we know its mass?
From the objects going around it, orbiting it.
Exactly.
Yeah.
So we're measuring the force.
We're measuring the
and
force.
Extrapolating the mass, the energy. Well, that's exactly what I did with the proton, right?
Yeah.
I
Strong force. Yeah.
It is exactly the force of a proton black hole would exert on other protons. One of the objections in my early equations is that, well, you know, the strong force has a really short range. That is, if gravity has a longer range, but the strong force, as soon as you scatter a proton, it drops really fast. It's called a Yukawa potential because it was Yukawa that wrote those equations. And so that was an objection because it's like, well, if it's gravity, why is it dropping so fast, you know? And that takes it to the paper that's in peer review right now. Like, it's been in peer review for a year. I'm kind of really happy when it's gonna come out. Okay, but and I'm gonna pre-publish now. It's gonna be soon. But basically, what happens is that what produces the force is the electromagnetic fluctuation of the 0-point energy, right? Well, imagine that thing is spinning, okay? And it's like a little vortex, like all these little point of 0-point energy, all these particles of 0-point energy, what I call the Planck plasma, right? Well, at the boundary, it decoheres very quickly. It loses its energy very quickly, you see? And so at that boundary, the energy drops very quickly, so the force drops really quickly. So then we calculated that, like rigorously, using Einstein field equations, and it gave the correct answer. It gave exactly the range of the strong force with the residual strong force, which holds the other protons in the nuclei, like far away from the proton. And then it drops again, and then it gives gravity at a longer distance, the gravity that we measure. So actually, gravity is not so weak. You see, in current physics, we say that gravity is the weakest force. Because,
Yes.
you know, the teacher goes like this, look, I can jump, you know. So it takes the whole gravity of the Earth and I still can overcome it. But if you put a physicist on the surface of a black hole, good luck jumping, you know, good luck, right? A black hole proves that actually gravity is the strongest force because at the black hole horizon, it overcomes the electromagnetic force and everything else. And you see, so um, so actually, it connects the gravitational force that we think is weak, which is actually just weak because we're always far from the event horizon, and connects it to the strong force at the nuclei level. And it gives the correct answer. But what I mean by the correct answer, it gives precisely the right answer, like very precisely the right answer. And from that answer, I was able to predict the radius of the proton precisely in 2012, which was 4% smaller than the proton that was being measured at the time. 4% in quantum physics is huge,
Yes.
because numbers are known with like 10-digit accuracy. Um, and then they measured it more precisely, and they realized, they had made corrections to the interpretation of the data using the standard model and give the wrong answer. And so they removed that, and they got the same radius I got. And so all the experiments since then, the radius I predicted is inside the margin of error of the experiments. And in 2018, it became the co-data value, which is the institution that gives all the official values for all fundamental constants. So,
Okay, yeah, I just want to highlight to my audience like how big a deal that is, right? If you think about how many decades did we use the proton in so many experiments, how many decades did we use a very specific mass, a very specific radius of the proton, and all of these, supposedly the most accurate theory ever, right? The most accurate, yeah, model of the universe ever. We used a very specific to many digits radius of the proton
accuracy. Yeah.
of accuracy, and so you were able to, using this different perspective, right, using the same math from Einstein and the previous physicists, like you said, you just used the strong force measurement of the strong force and thought of a proton as a little tiny black hole. You were able to predict a more accurate radius of the proton. So this is really unbelievable to me. It seems like this should be Nobel Prize material. I don't know. Is it? Is it just me? I mean, is that? What did they say?
So too, but
Yeah.
I don't know.
Yeah.
It's not my, my, like, I'm not, like, if they want to give me the Nobel Prize, I'll be happy, mostly so that it's easier for me to publish and be
Yeah.
listened to. That's
sure.
the main thing. That would be really useful, because I think there's a beautiful gift in this understanding, like, that goes way deeper than, like, oh, you found new mechanics for the proton or the atom. That like is really profound, both on the personal level, like of our understanding of ourselves, the universe and everything, but as well in the technology we can develop from understanding this fundamental principle, because it tells us something much deeper about what gravity is and how the material world emerged from the relationship between gravity and the electromagnetic field. This is, that's what we started with. Yeah.
Exactly. And so that happened in 2013. You released that paper?
Yeah. So, I sent it to the Library of Congress on December 20th, 21st, 2012. And then it took a while before it got published. So it has a 2013 date, but, people can go and see on the Library of Congress. That's when it was filed. And the new measurement occurred. So there was an earlier one in 2010 that had got that shorter radius, but everybody was poo-pooing it. And, they were saying, it can't be, there's an error in the math. You guys did something wrong. But in 2013, they confirmed the shorter radius. And so that was in January 2013. And my paper only had been out at the Library of Congress for like a few months, and or a month and a half, and yeah, it was inside the measurement, like very nicely inside the measurement, and then there was a lot of debate. It was like uproar in physics. The rate is the proton. Oh my God, what's going on? And all this. And it took till 2018 before, they actually did new experiments, not with muons, but with electrons, like normal scattering. And they realized that when they looked at the earlier experiments with electrons, that these corrections that they were putting in from the standard model was what was tweaking the result. And so they removed it, and they got the same radius, and then they made it the standard radius. Yeah.
Okay, so it's still this is amazing to me. So what I understand is that gravity, what we understand of as gravity, is the strong force, just at a different scale. Is that basically what you found? Okay, so
exactly, and so is the Planck force, meaning, the Planck scale has a force too that was computed from all the math, all the equations. And that force is way, way stronger than the strong force even, right? And what's beautiful is that the scale from the Planck force to the color force or the strong force is exactly the same from the color force to the gravitational force. It's called alpha G. It's the same ratio. And this is the ratio that Einstein and Rosen had found, but didn't realize what they had done. And that ratio was found by other physicists like Rees and Carr published a paper in Nature in the 1979 showing that when you look at all the objects in the universe, you keep finding that same ratio across the universe, right? So that you can see that actually space-time is pinching at very specific relationship ratio. And it's this fundamental ratio, kind of like the way space-time organizes itself to produce all of our world and our universe and everything. And it's crazy because then you can study the little proton. And when you study the little proton, you can output the mass of the universe, its temperature, its size, right? Because now you know the scaling, right? It's amazing. And it gives the right answers. Like it's very, very accurately in what we observe.
And so this, I guess, would also explain Dirac's famous large number hypothesis, right?
Hypothesis, exactly. Dirac had figured it out. He could see it, but he couldn't figure out exactly, where does this number come from? Like this 10 to the 40th orders of magnitude, from the Planck force to the color force is 10 to the 40th to the gravitational force is 10 to the 40th. So these are huge numbers. That's the other thing that's crazy about this theory, because you're using huge, crazy numbers and you're nailing with high accuracy, the little proton, its mass and its radius and, its force and everything.
So when you... And I guess, what is the color force? Can you describe what the color force is? Is that the electromagnetic force?
No, the color force is so since when we discovered that the protons are positively charged, So they have an electrostatic charge that's really strong. Like if you try to bring two magnets really close together, like that are like strong magnets, and
Yeah.
they're the same charge, you can't,
Yeah.
it will always look, it's so
And this is
strong, right?
the problem with fusion, right? I mean, this is why we're having
Yeah,
issues with fusion
that's
and
right.
yeah.
That's right. They can't overcome the electrostatic charge and get the protons to fuse, right?
Yeah.
It's
Right.
it's so strong. They just can't get it to, I mean, they get a little bit to fuse, but they can't sustain it. It requires so much more energy than the energy you can get out. And
Yes.
so this is, and so this, when they discovered this, they're like, okay, well, what's keeping the protons together? There must be some kind of strong force.
Yeah.
And they literally called it the strong force.
Yeah.
And then later on, they realized that the strong force is just the residual, like the strong force in the nuclei that's holding the protons together is just the residual force of actually the internal force that's inside the proton. And that's called the color force.
Okay.
And it comes from in their formalism, it comes from a gluon field
Okay.
that's gluing the protons together,
Got it.
and the quarks, and so, but this, as I was saying, is not analytical. It's a whole lot of hand waving,
Okay.
and where this solution is classical, it's actually fundamental, it's first principle, right? It cannot be wrong. If it was wrong, then all of physics would be wrong. If this
Yeah.
is wrong, I assure you, quantum mechanics, general relativity, it's all a fluke. It's if this is a fluke, then it's all a fluke.
Okay. But like Dirac's large number hypothesis is
Yeah.
the electromagnetic force um, over related to gravity is 10 to the 40 difference, right? So what we understand is of a proton, positive, like you said, how can it hold a little electron in its
Mhm.
orbit? So that
Mhm.
is the electromagnetic force, I guess. If you relate that to gravity, the problem is it's 10 to the 40 different. And
Right.
so I think that was the big the conundrum, right? Why is that so different, that force?
Right, exactly. And why does it drop so fast? It's not like gravity that reaches much farther. Why? Like if you scatter proton, like as soon as they separate a little bit, the other proton is free. And
Yeah.
like so, the range of the force seemed different than gravity, and all this, and all that is true, and the result is that they build this whole other framework mechanism to try to explain all this called QCD,
Okay.
which doesn't give closed form for a solution. You know, but because they had removed 0 point energy, as soon as you put it back in, then you understand it's curving space time, but it's called a screening. The electromagnetic field can get screened, right? It decoheres. And when it does, well, the gravitational force decoheres with it and it loses a lot of energy. So the force drops very quickly. So it, it really kind of like puts quantum mechanics and general relativity together. 0 point energy, Planck scale physics with general relativity to explain in general relativity where mass come from. It can't
Yeah.
just be, oh, you just throw a
It's
mass
a
in the
given.
universe. Yeah,
Yeah.
you can't just say it's a given, right?
No, that's my biggest complaint, and why I say modern physics is bunk essentially, because they can't explain where inertia comes from.
Right,
Where does mass come from? They just can't explain it at all. It's just a given. They say it's
right.
space time. That's it. So this would really solve. I would say is the fundamental issue with
And
modern
charge.
physics. And
Yeah,
charge.
and charge.
Yes.
Yeah, they can't tell you where charge come from, right?
Or even
And it comes
radioactivity.
yeah, it comes out of these equations. That's the part I haven't published yet. Okay,
Okay.
it's on its way. It comes out of those equations. The source of the electrostatic charge comes out, right?
Amazing. So, well, what is holding an electron in to a proton? What force in your model?
It's the so the electron um, the electron relationship to the proton is of attraction, right? Because the
Yes.
electron is negative, the proton is positive. But you see, let me try to explain it the best I can think of. If you look at a galaxy, right, you got a black hole in the middle. And it's not because you have a black hole in the middle that all of the stars around it are crashing into it, right? Why?
They're in orbit. They have velocity perpendicular.
That's right. Exactly. So you have a little black hole proton that's spinning at the speed of light in the middle of the atom. Okay, and it's in a Planck plasma. It's got electromagnetic. It's in a fluid. Like think of like if you got molasses and you're spinning the molasses, the stuff around it is going to start orbiting, right? And it's going to make other vortices and stuff. And so more you have these little spinning things, more vortices you're going to make around it. The electron is in orbit. You see, the problem they had is that an orbiting particle should radiate its energy. This is the problem they had with the electron. It should like radiate its energy and, it should lose energy. It's not just really spinning. And then it should crash, right? Because it can't stay in orbit, right? So they, in some ways, arbitrarily invented quantum numbers and made spin not spin. It's like, okay, we're just gonna make like it's not spinning, although we're using, geomagnetic, equations, and we're using all this and all this that has spin in it, but we're just gonna say it's not spinning. It's just a cloud of probabilities, right? And and this is when quantum mechanics went sideways, right? It went like and the Copenhagen interpretation all of a sudden, like reality can just like you can have cats that are alive and dead at the same time. You can, and everything goes crazy esoteric, man. It's like you can't believe this is. You know that when Schrodinger came up with the cat is alive and dead at the same time,
Yeah.
he was actually trying to make fun of
Yeah,
the
it was a joke.
interpretation.
Yeah.
It was a joke.
Yeah.
And then it became the standard.
It's so ridiculous. Yeah.
It's mind-boggling. A whole
Yeah.
planet, a hundred years, thousands of physicists, like the best minds in the world, going around repeating that cats can be alive and dead at the same time, and it's
Yeah.
like until it's observed, until it's
Yes.
measured.
Until it's measured. It's just too complicated. You can't understand. It's just too complicated. That's why you can't understand it.
Exactly. Shut up and calculate. That was
Yes.
what Feynman would say. And it's just like, no, there's probably something that was missed.
Yes.
Okay.
Probably.
We just probably missed something because who's making the measurement? What about the flea on the cat? Is the flea on the
Yeah.
cat point of view is that doesn't matter, or what about the microbes in the box? Oh,
Yeah.
the universe is confused about the state of the cat
It's
because the
confused.
human hasn't observed it yet. Right?
Yes. Yeah. Until it's
Oh my God.
observed. Yeah.
Yeah, it's so human centric. It's
Yes.
remarkable. Oh my God.
It's ridiculous. Yeah.
Oh my God. I just couldn't believe it. I couldn't believe it. And I'm not like being mean or making fun. I'm just, it's I think it's important for people to understand that like we make the best assumption we can make with what we have, but if you go to the root of what was missing, so that we don't end up with cats that are alive and dead at the same time.
Yeah.
When the electron is going around, it's being fed by a field of energy that is the 0 point energy. You see, if you don't have a source of energy, of course it's going to radiate all its energy within billionths of a second, and the atom is going to stop existing, right? But you can actually have real angular momentum if you have a source of energy that's keeping that thing in orbit. Do you see the difference? So as soon as you remove the field of energy, the fundamental field that sources everything, then the whole thing stop making sense. But as soon as you put it back in, then okay, it's radiating energy. We call it the energy of the electron, but that's because it's getting the energy. So one example, when I wrote these equations for the proton, then I calculated if the proton's a little black hole. I know this is like shocking for most physicists that are listening to this. They're going to be throwing tomatoes at their TV, like but I assure you it's correct. But anyway, so if you take the proton, you make it a black hole, and you calculate the Hawking radiation of that black hole, that's the energy that's radiated by the little thermodynamics of this little black hole. You get exactly the rest mass of the proton. So you've got the rest mass of the proton twice. You got it from the standing wave of the vacuum fluctuations inside the proton, and you're seeing that it would radiate exactly the same amount of energy out. So guess what your proton is? It's hyper stable, right? It's never going to lose energy. It's always going to have energy. It's radiating always the same amount as it's receiving. So it's super stable. And what do we see? We see proton like crazy stable. We've never seen a proton stop its thing. Like they don't just run out of energy. Since we can see as far back as the Big Bang, we don't see one proton losing, just disappearing, right? It's so it's the same thing for the electron. The electron is fed, the angular momentum is conserved from the proton to the electron, and so on. And it's fed by the vacuum fluctuations. And when the electron is freed, as it's traveling, it's fed by the vacuum fluctuation. And actually, inertia is the resistance of the vacuum fluctuation to the movement of an object.
Okay.
It's the exchange of energy between you and the vacuum when you're pushing your fridge, right? And it doesn't want to budge,
Yes.
So this, you see?
Is that so? That does make sense to me. So the proton is spinning at light speed, and so it's giving off energy exactly equal to its rest mass. So is that where the inertia comes from? Is basically it's emitting that amount of energy in all directions. So it's
That's
basically
right.
So that's where the rest mass comes from, is the emission of that
Exactly.
energy in a sphere, essentially.
Yeah, exactly. And that's what we
Awesome.
measured. And that produces the charge radius of the proton, where the charge is, and that's what I predicted, and that's what I came in like 10-digit accuracy in, right?
And that's the Schwarzschild radius, right? Is that what you calculated? That actual radius was based on the Schwarzschild radius, which is the radius of a black hole.
Yeah, the radius of the black hole is at the Compton scale inside the proton, and then the charge radius is exactly a factor of 4, which is really interesting. From the Compton radius. The Compton radius is where, and that gets us. Let's finish this discussion because that gets us to a better interpretation than the Copenhagen interpretation. That comes from Duboglia, writing his PhD thesis saying particles, can be described as waves.
Yep.
Yeah. And he had all kinds of troubles passing his PhD with that. He got in all kinds of troubles. Eventually, his director of thesis sent his thesis to Einstein because he's like, I don't know if this has any validity. I need somebody like you to tell me. And Einstein said, well, actually, he shouldn't just get his PhD. He should get the Nobel Prize with it, which he did in 1927, right? But that so the Compton wavelength is like is where the fluid dynamics of the Planck plasma is occurring, right? Which some people looked at my equations, which predicted the charge radius, and said, because I didn't mention the Compton wavelength in my paper in 2012, so I skipped that, and they say, oh, well, it's just a factor of 4. Basically, you just found a factor of 4. It's irrelevant. Never mind that I was able to solve Einstein field equation with the Planck plasma itself, and because the mass is in the Compton radius, they say, well, the mass is in there. So, but I was like, no, but these equation tells you where the mass came from.
Yes. The mass is already there.
It's not just a free parameter in my equation. And so if you follow Duboglia's thinking, okay, when he's saying a particle is a wave, what's waving?
Yeah. What's waving? That was my next question. What is light? That was my next question. But what is waving exactly?
What's waving?
Yeah.
And so basically, eventually Bohm takes that and goes, hey, wait a minute. We can interpret the double slit experiment and the Copenhagen interpretation using Duboglia's equations and describe what's called pilot wave theory now, where instead of the particle being 2 places at the same time and because all this crazy quantum weirdness, you can actually describe it as almost like fluid dynamics. The particle is being led where it's going, and by a pilot wave, by the waves of the structure, right? Pushing it. And so if you have one slit, you have one particle, it's hitting the backboards, making dots. If you have 2 slits, the wave goes through the second slit, interfere with it, and you get interference. And if you observe, you're making waves in the field too. So those are
interfering.
Interfering. So of course you get a different.
But we measured it. No, we measured it. We observed it.
Yeah, but it's not magic. It's just fluid dynamics,
Because you're interfering, right? How do you measure? You measure by interfering with the wave.
Exactly. But the thing is in all this, nowhere did it say what's waving. And what we are bringing forward is saying, actually, what's waving is this fundamental field, electromagnetic field, that's at the base of creation.
No, there's no ether. La 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 la. No, the
Ether,
light is just,
no, no, no.
space. Space is nothing. There's nothing in space, Nassim.
Right,
It's
right.
just
Of
it's
course
just
not.
empty. There's nothing there.
Yeah,
And light
and
light is a
and
photon.
this device is
Yeah.
miraculously getting the information because there's nothing in space.
No, there's nothing. The sun
Yeah,
is just the sun is creating photons and it's sending those photons to our detectors, which we have never actually detected a photon, by the way. That's also interesting. We've detected the
yeah,
result of light hitting matter, what we call matter, and then we
right.
theorize and postulate that there are photons actually exist, but we've never
Yeah, that was Einstein, the
directly.
photoelectric effect.
Yeah, the
Yeah.
photoelectric effect. What explains the photoelectric effect if you have nothing to wave is an invention called the photon. It again, we've never detected a photon.
Well, we definitely can see this it's quantized. We definitely see that the waves come in packets. But you see, why packets? Because space-time is curving. You see, because there's encapsulation, because space, it's actually, because it's organizing the gravitational field. There's a flux that's going in and there's a flux that's going out, and that makes a boundary condition, a standing wave that produce boundary condition that encapsulate, you see, and that's why it's quantized. And this leads to really deep understanding of the nature of gravity uh, at the electromagnetic field scale, and that leads to gravity control. Like, I know that your show is very much interested in all these strange objects that float around in our space. Yeah, I think that it's really kind of, it's really, it leads there because the nature of gravity, just to say it's space-time, just doesn't tell you what gravity is, right? It just doesn't. It doesn't, like, um it just tells you, okay, you got some mass, some energy that just came out of nowhere, and it's curving this space-time metric, which is some kind of mathematical tool that we're not going to tell you what it's made of. And and clearly somebody figured out something else. Because there's things flying around that are not, you know, are not burning ancient dinosaur material to go around,
Yeah, I had a very interesting interview. I filmed it yesterday. It'll be released by the time this is released, so I can talk about it. But it's this guy Dan Isbell, and he was literally is a legend in the Air Force. He was a test pilot. He flew over 70 aircraft. His stories were just amazing. And
Oh,
he
I
had
can't wait to see it.
yeah, his stories were amazing, and he follows plasma physics. He's loves this stuff. I'm sure he'll watch this interview. I have no doubt. So very interesting guy, and he had 4 encounters, and this guy knows what to look at. And so when he saw this object, he said it basically was a large vehicle, a craft he called it, and flew in very fast and then just stopped. Like there was no slowing down of inertia. It just moved and immediately stopped. And there's always, he said it was coated and surrounded by some sort of plasma. It looked like electric charge around
Around
it.
it,
Yep.
electrostatic charge.
Yep. Exactly. And he had another encounter. It was very similar. There's always some sort of light involved. It was actually a craft right above him, and he said it shot him, or not, it engulfed him, I guess, in what he called defocused. It looked like a defocused laser. So basically,
Mm.
light energy defocused, and as soon as he saw it was there, he said, "Wow, that is what is that thing?" He said again, as soon as he had that conscious thought,
Yeah.
it enveloped in a field again of white plasma, and it was the size of the craft, which he couldn't tell how high it was, but then it immediately quantized again to double the size in a plasma ball, and then he said
Wow.
it quantized again to four times the size, and then
Wow.
immediately shot off as faster. He said faster than you can imagine. And again, there's no sound, there's no sonic booms, and
It was
his
like they were revving their engines,
yeah,
right? They were revving the engines, and the thing was getting bigger as
yeah,
it produced more power.
something. And well, he said they must be getting the energy from somewhere. Like they don't have
Yeah,
a big fuel tank. Is it was his argument is that they were pulling that energy from somewhere. They were basically absorbing it from, and this makes
from
perfect
the
sense.
structure of space. Yeah, of course. Yeah, yeah, of course. The universe is full of energy. Like it's hard for people to feel it or to understand, like, because even in this case, like, you use your phone and you don't really think about it, but there's like electromagnetic waves flying all over this thing, and but we think of it as just empty air. We don't, like, and it's the same thing, like, if but these wavelengths are super long, like they're like the universe for the Planck scale wavelengths. For the Planck scale wavelengths, it's so the fact that you can't feel this, right? The frequency is too high for you to feel it, right? Well, imagine the Planck scale. You're not gonna know it's there until your equation tells you, and then you might even miss it for 100 years, although your equations told you.
When you said that the inertia was a result of resistance, basically from the ether. I've had this same. I've been trying to find this thought as well. Is I had the speculation, I guess, that the redshift that we see, the cosmological redshift, could this be due to some sort of resistance um, with the ether or the 0 point?
Yeah, that there is cosmological theories that actually says that it's birefringence property of the vacuum that produced the redshift and so on, and there is on this resistance to inertia thing. I mean, there is electrodynamic theories that were brought forward in the 70s, that were very much talking in those terms. Those as well were kind of thrown away for some unknown reason, although they were doing good predictions. There was and there is as well, if you look at, you remember Hawking radiation. If you look at Hawking radiation, well, there's an equivalence to equations that describe the same as Hawking in some way. Like, yeah, I mean, it gets the same answer. It's called the Unruh effect, where actually, the movement of the particle through the field creates self-inducing, thermodynamics and so on. And so it's kind of present in there. It's just not being understood. And again, you remove the field, you remove this fundamental fluid from space-time, these electromagnetic fluctuations, and all of a sudden, like, your physics are very kind of like broken. And if you Yeah, if you look at my equations, actually, I didn't invent anything new. I just rearranged. you know, I just I just rearranged what was already there, and it gave the correct answers. I'm not coming up with like 11 dimensions of strings. I'm not, I don't need membranes. I don't need,
But you
these
changed the fundamental
strange
assumption.
physics.
You
Yeah,
changed, I argue, the biggest assumption where we went wrong from Einstein is we assume that space is empty, that there is no fundamental medium, that light
right.
is not actually waving anything. It's some new entity and it has a dual nature where we just now we
Yeah,
went. So now the cat is alive and dead at the same time.
yeah, exactly. And it's present, and people say, well, like Markinson and Marley experiments, and all this, but these experiments were like, it's crazy. They were trying, like, the idea that you could measure it this way, first of all, at that time is like that you would measure an ether draft, like it, it was not consistent with actually what ether would do. But basically as well, um, we it's crazy because it comes back. And this is why Einstein eventually said, actually, my equations are inconsistent with an ether, is because it comes back, this idea that the ether would drag behind an object, right? It comes back because it ends up in Einstein field equations after linearization, um, uh, by it's called space dragging, or space-time drag, or frame dragging, or even like lens steering, for instance. And so you when you look at this, you're actually, and we measured this, right? Like, we put a bunch of disco balls in orbit, and then we shot lasers, and to try to see if they were losing rotational speed relative to the Earth, and we measured that it was dragging behind, and then we sent a probe that cost, I don't know how many billion, and it took like some 20 years and whatever. It was called the Gravity Probe B, that measured the frame dragging of space-time, but it's never all been put together. It's kind of crazy. It's it, it's I mean, it's because it's in different parts. That's what I mean by I took each part and then I stuck them together in a different order, and I got a different answer. And that answer, I think, is very powerful because it comes from first principle. All of a sudden, you're not doing anything weird. You're just doing physics, really.
Yeah, and I think it's other people have not come to your analysis, your level of accuracy, but I think many other people have had the same thoughts and feelings and
Oh yeah.
basic theories. It was Salvatore Pais. I interviewed him, and he had the same argument. He said that there is one scalar force, which he calls the superforce, and it's c to the fourth over g is what he calls
Mhm.
the measurement of it, and he says that scales
Well,
at
that's
all
the strong
levels.
force. That's the strong force. C over four, C to the fourth over G is the strong
Is
is the Planck force.
the Planck force?
He calls
Yes,
it, yeah, that's a Planck force. Yeah.
he calls it the superforce because he said it scales at all levels, out to the universal scale. And so I think
Yeah.
you've just had what appears to be the most accurate that I've at least come across and seen
Mhm.
representation. But I think other people have come to a similar conclusions. I called it the
Yeah.
love force, LUV. You have Einstein has GUV, little GUV,
Right.
So I called it LUV. Basically, that light matter is made of light, which that is spinning. You have a proton would be a little black hole because it's in its own little radius. It can't escape
Yeah.
that. And
Yeah.
light, but my argument is light is attracted to light, essentially. So that's why when it comes close to another entity that is light, it will attract to it. So I called it the love force and measured it with LUV. But again, the same. It's a same idea. I think yours is You came to the where does it come from? But I think this idea of one scalar force is a
Yeah.
makes sense.
It's funny because I think it was, uh, I can't remember what year, maybe like 2000, no, 1998, maybe. Um, and I was at a physics conference in Nebraska, I think,
Awesome.
university. And, it was a private conference. So, and then we did a press release after, but it was all private. And I announced that I had found a new particle and I called it the Lavon.
Awesome. Yes.
Because you have the
I'm
glue
sure they took it well.
so,
I'm sure they took it just like they took my theory, Nassim. You can't put love. Love is the most powerful thing in the universe, and yet you can't put it. You can't put it into a theory, or everyone freaks out. So, that's awesome.
yeah.
I have
You
one
have to
thing. Oh,
laugh, otherwise you start crying.
exactly. Done both. Don't worry. At the same time. Um, I have one thing I've been struggling with. I would love to get your impression. Is we hear all the time about the James Webb Space Telescope, right? And it looks they say back in time, and again their predictions they're wrong repeatedly. And what we're seeing is we're still seeing galaxies back to very high redshifts. And I think if you look at the universe with that there is a basic medium, it leads to many extrapolations, right? That the universe, what I found is that space is very likely not expanding. The redshift is due to other interactions, I believe, as we've talked about with the medium, with the ether, or the vacuum. But what is
Mhm.
so? What is the structure of the universe? Why are we always in the center, every direction we look? And what do you predict we'll find? Let's say we take the next telescope, which can see even further to the left in frequencies than James Webb. Will we just continue to see more galaxies? So I guess what is your thought on that? Does it relate back to the holographic fractal universe?
Yeah, I mean, that's one thing that was really stunning and that got me in all kinds of trouble. Is that when I did this calculation for the proton, initially I did it with just geometry. And I found like the solution to Einstein equation with the geometry, meaning just with the Planck plasma. I call them PSU, Planck spherical units. So like it's like the grain of the Planck plasma. I refound the Schwarzschild solution to Einstein field equation. But when I was doing that calculation, I calculated how many of those little PSUs are inside a proton cavity. And because Plancks are so small, there's 10 to the 60th PSUs inside one proton, which is a volume of 10 to the minus 39 centimeter cube. So it's pretty damn small. But, these Plancks are so small. And then if you multiply that number of Plancks by the Planck mass to figure out the mass of all the little Plancks inside the proton, this would be the modes that are canceling and the mode that are constructive. You get the exact, what's called the critical density, the density of the universe, the exact mass of the universe, including dark matter and dark energy, like including the whole thing, right? So you don't need dark matter and dark energy. You're predicting the correct mass. Um,
Could calculate the critical density from that geometry.
right, from the proton. And, and and then when you do that, you stick it in the observable universe, okay? That the radius we see, and you get exactly a black hole.
Right. I've noticed this, not in the direction you found, but if you take the mass of the universe and you determine
With
the
dark matter and
radius,
dark energy. Yep.
everything included, that the universe miraculously, based on the mass that, like you just mentioned there, I think it's 10 to the 58 kilograms, something that
Yeah,
magnitude,
exactly.
that
Yep.
you get the radius that we can physically observe when we look out with our
Right.
telescopes, which is that is
Right.
amazing. That is the Schwarzschild radius. I told
Right.
Pais that Salvatore Pais did not know that, actually, so I was happy to.
Really?
Okay, he knew about it
Oh,
at the proton level. That's where he
yeah.
found, just like you've talked about, but not at the
Oh, okay.
universal scale. Yeah,
Oh,
so that
wow.
is amazing. So you can,
Yeah. So
based on
to
the
answer,
proton density, you can get the
yeah,
Schwarzschild radius of the universe.
based on the proton quantum vacuum density, right? And so now you have you have an electrostatic gravitational boundary between the internal pressure and the outside of the proton, which defines the horizon of the proton. But when you're looking at the universe, then you can apply what you see in black hole physics, out, like, in the galactic centers and all this, to the universe. If the universe is truly a black hole, then it should have the same dynamics. It should be spinning, okay, which has been a battle of mine since the beginning of doing physics, like 35 years ago. Like, there's a good chance the universe is spinning, since everything in it is spinning.
Yeah,
um,
which they
and
just found, actually. Yeah,
Yeah, which they are now finally, seeing. Oh, well, there's all these galaxies that are spinning in the same direction, must be
yeah,
from a universal spin, and so on. And so then you're gonna start thinking, okay, well, then it must have, like, the same dynamics you see around black holes. You can imagine it has, like, um, um, uh, toroidal fields, and all this, and then you start to think, oh, okay, the universe may be expanding still, but it might not be that simple, meaning that, like, you can have, it might be more complicated, than just, oh, the universe is inflating like a balloon, right? Meaning you can have circulation inside that makes it so that everything appears to be going away from you, right? Like, if let's say you're inside a torus, and there's more and more evidence that the universe is a torus as well, from background radiation and so on. And so let's say you're in the torus, you're at the equator of a torus, you're moving away from the center. Just like at the equator of a galaxy, stars move away from the center. All the stars are moving away from each other. So you might think the universe is expanding, but you're actually just moving inside the universe. You're orbiting inside the universe. And so you see the galaxies moving away from each other because they're, like, circulating inside the universe, right? And um, and that can be combined with the fact that the universe is expanding. So now when you're measuring with the redshift, and when you're measuring with other instruments, you might start getting, like, different values, and now you're confused, and which is exactly what's happening now with the James Webb Telescope and so on. Like, we're getting different values. We're not sure which one is the correct one, because it's a little more complex than just a balloon expanding, right? It, it, it's it, and And we think we're in the middle everywhere we look, just because as we're circulating, everything appears that it's moving away from us. So of course we're observing from us. So observing from us, everything appears like is moving away and we're in the middle. But that's just because there's circulation going on.
How do you describe then the cosmic horizon? That basically every direction we look, we can't see past the same basic point, same distance. We call
Right.
13.8 billion years.
Yeah, well, that's because when you think of like the center, like you're observing and your limit is the speed of light.
Yes.
Right? Meaning anything that's past that limit, you're not going to see.
Right.
The light doesn't have time to get to you, right? So from that point, anywhere you look is going to look like you're in the middle.
I see.
You
So,
see? Because
I guess I assume that if the universe is a black hole, then what we would see at the edge is the event horizon, essentially the boundary of the universe.
well, you're inside the black hole.
Yeah.
You're not on the outside looking in, right? You're inside the black hole. So there's a difference there. You know, you're on the side where actually light is going in, right?
Yeah.
And you're expanding out. So that's what I mean. It's more complex. You can't just reduce all this to a balloon, right? It's a little more complex. And that complexity creates all kinds of difficulties in, the way we measure things. But having a fundamental model that you can extrapolate from the small,
Yeah.
then that gives you a good idea of what's going on. And now you can start to put things in the right order. You see, for instance, you would expect that they would be like structures, like the big void, you would expect, you would see big walls, and like all these things that are like not homogeneous. You would expect like what they call the big axe of evil, where it seems like there's an axe to the universe,
Yes.
right? Which is probably because it's spinning, and because we're in that, just like a galaxy. Think of a galaxy and just grow it to the universe, and you got probably something really close. That's why there's black holes in the middle of every galaxies.
And how do you describe then the galactic spin? So can do you need dark matter in your model, or I'm assuming that
No,
there's no dark matter?
no. I didn't publish that part because, again, like I'm trying to publish as fast as I can, but
Yeah.
it takes years, because let's just say it's been difficult. Let's just say that. Okay. But yeah, no, I solved those equations. I can account for the way galaxy behaves, because in my case, I have 0 point energy producing gravitational effects. And so if you put that in and you actually solve those equations, then actually you get exactly what a galaxy should look like. You don't have to invent some dark mass that's curving space-time, but not interacting with the electromagnetic field at all.
Yes.
And being exactly in the right quantity so that your equation work. I don't need to do that. Yeah.
Is it the same basic idea that we talked about earlier, where the fall off distance of the strong force
exactly
is different from what you're assuming?
Very good.
So that's the same relationship.
Yeah, exactly. Wow, that's amazing. You figured that out right there. You're impressing me, bro.
Awesome.
Yeah.
Oh, cool.
You
That
must be
makes sense.
surfing.
I surf. Yeah, I do surf. Haven't
So you
haven't lately.
understand. Yeah.
Okay, quite cool.
Yeah. So yeah, exactly. You apply what you're seeing at the proton scale to a galaxy, and you get the right answer. You don't need to add mass, um, and and it really
Because it's
makes
force.
it.
Like you said,
Yeah,
we measure the mass through the force that we're seeing. So if it's a
exactly.
misunderstanding in the force in our models, then that would make
Mhm.
sense.
Yeah, exactly. So, I mean, really, when they add dark matter is because they have to add force. They have
Yes.
to add gravity to the thing so that the stars don't fly out because the galaxies are spinning too fast. The stars should fly out.
Yeah.
So they add dark matter on the outside, you
Yeah.
know,
And a
on
halo.
the halo. Yeah. And they add like 80% more mass, right, in dark matter
Yes, it's insane.
so that the equation solves properly. But actually, if you consider that, you see, like a galaxy is like a cup of coffee. I don't know if you drink coffee. I don't,
Yeah, a
but
lot. Yeah.
I watched my mom drink coffee my whole childhood. So I know she was Italian. She liked her coffee really black. And so she would spin it. And it always kind of drew me in when she would spin her coffee and then take the spoon out. And you couldn't tell that it was spinning because it's so black. You can't tell that it's spinning, right? Like you barely see the little dimple in the middle, right? And then she would pour the milk and it would make a galaxy, right? It would make the arms of a galaxy. Like so basically what we've done is that we've accounted for all the material of the milk, but ignored the coffee. So of course we're missing 80% of mass, right? The galaxy is actually a phenomenon of the vacuum fluctuation spinning in that region of space, just like a proton is. And the stars and the dust and all this stuff that's stuck in it is what makes it appear as a galaxy to us. It's the dust and stuff. But you could remove all that and it would still be a vortex of space-time spinning, in that region, right? We only see it because stuff is stuck in it, the milk. So if you calculate the milk without the coffee, you're going to miss a whole bunch of the forces you need.
Well, there's one other physics really interesting point that I'd love to get your take on is I was surprised to learn rather recently actually that if a neutron is outside of the nucleus, you mentioned a proton, extremely stable as far as we know, stable since the universe has existed. But a neutron, if it's outside of the nucleus, will decay in like 10
Yeah.
minutes. Where
Yeah.
does it go? Like what is happening to this neutron?
What does it decay into? Do you know?
Yes. Uh, it's an is it electron and a no, I don't know.
Yeah.
Off the top of my head. Is
An
electron and a
electron,
proton?
a neutrino, or
Ah,
anything,
okay.
but then what does it decay into? What does it end up being? It's a proton.
Oh, so it is. So a neutron turns into an electron, a proton, and emits some radiation. So yes, I was on the right
Yeah.
track.
So it just goes back to the state of being a proton,
Okay.
right? And so a neutron is a proton in disguise. It's a, a neutron is so imagine you have a flux, okay? Because I'm only talking about the hydrogen atom, in my equations because it's the most simplest. It's only got one proton. But the table of elements, you can have like a whole bunch, like 60 protons, and so you've got all these black holes spinning in this flux of electromagnetic fluctuation. They all, it's a dynamic, super high energy thing, right?
Hmm.
I mean, no kidding, it's a super high energy thing. When you break it, you get some
Yeah.
serious juice out of it, right?
Yeah.
You break the nuclei of the atom,
Yeah.
with a little few kilograms of matter, you make an explosion that, like, wipes out a whole city, right?
Yeah.
And so it's a very highly energetic thing. So imagine, so now all the polarities of all these little protons, working together, like spinning together, produce region where the protons are in neutral state. They all cancel, the charges cancel out. So you have neutral state. But it has a lot of angular momentum. It has the energy of the whole nuclear spinning. So when you scatter one out, that energy's got to go somewhere. It's radiated out. It makes an electron in the fluid dynamics of spacetime, and the rest is called a neutrino, right? It's when they tried to calculate the energy, they ended up with a little bit of energy left, and they called it a neutrino
And
that's emitted.
I
The
see.
proton goes back to stability. And it's the same thing in an accelerator when you collide protons, right? You get little chunks out. But then the proton reconstitute.
They
Right?
reconstitute.
Yeah, it reconstitute in some cases. And so basically, um and this is okay. You want to know the funny part? I'm gonna get in so much trouble for this interview,
I
but
love it.
that's okay. This because I'm just telling you, like, my most profound thoughts.
I love it. No, I
Okay.
really appreciate it, Nassim. I love it.
The we built accelerators to try to probe the atom to figure out how it works and what is it made of and all this stuff, and it was a good idea, like to, like, kind of like knock things together and see if we can get parts to come apart a little bit so we can open it up a little bit. I think that approach was valid till we got to the proton. We scattered a proton and we got a neutron. I think it's valid. Anything past that, I think, is generally, like, the standard model of particle physics, I think, is generally invalid. And I'll tell you why. I talk about the proton like it's a fundamental particles, and physicists, kind of like get upset with me because and they say, oh, he doesn't even understand that the proton is not a fundamental particle. And I always laugh at that because it's like, well, you know, um, what I call fundamental is something that is stable, right? If I'm looking for the building block of the universe, I'm looking at pieces that the universe makes that builds the universe out of, right? So these pieces it makes, they should be stable, right? Okay. Now, when they tell the world that when they break the proton, they get all these particles that are more fundamental than the proton. But these particles decay. The ones that are the longest lived decays within 10 to the minus 8 seconds. Those are very long, particles. And the ones like the Higgs mechanism decays in 10 to the minus 25 seconds. Okay. So in, like, the blink of an eye is like an eternity for those numbers. Okay. And so I can't even say they're gone within the blink of an eye because that's way too long, right? So so they, where do they go? They go back to the vacuum. They if this was a fundamental particle, the universe would recognize it as such, and it would be stable. It would go, oh yeah, this is part of what I do. I make these, right? But it doesn't. It really doesn't. And it really is, like, it's really difficult. I mean, I'm going against a huge, enterprises, right? I mean, we're talking the largest experiments on the planet. It's not against, I'm just saying this should be re-examined, right? Like the premises that what, so, they've built a whole framework, a whole theoretical model, a whole thing to describe these particles, to describe the energy of these particles and all this. And it is very precise and it does a really good job at describing them. But what are we describing? Right? Is it actually fundamental, or is it only fundamental to the theory that describes it? Right? Because when, for instance, you take the Higgs mechanism and you apply it to the proton, which that one is stable, right? That one is a building block. Well, you only get 1% of the mass, or 1 to 5% of the mass. So, like, and so this is really kind of sensitive point. And again, I'm not being facetious or not, like I'm just pointing out that, like, this might not be like the best mode of exploration for things that are beyond the proton scale, because according to what I found, you'd have to get almost to the Planck scale before you'd see something stable again, right? Then you would find another building block, because it is the building block for the proton. And of course, I pushed the equation further and found the building block for the Planck, right? Because it's fractally divisible, and so on.
I found a similar thing is basically every 10 to the 21 size changes is what I saw, where you would have a repeat of a system. So if the proton is at 10 to the minus 15 meters, then if you go to 10 to the 6 meters, that's basically the size of a planet.
Very good.
Is it something like that? Do you see stable structures?
Yeah, this is the scaling law that Carr and Rees published in Nature. This is like what I found. You see, the 10 to the, if you did the calculation like precisely on things that we measure more precisely, you would find it's actually 10 to the 20th, which is it's the geometric means of the 10 to the 40th, you see? And so it's the square root of alpha G, right?
The square root of alpha G. So that's where you're getting that scaling size.
Yeah, exactly. And it's like if you go from the black hole energy of the proton and the rest mass energy of the proton, you get, in the geometric means, you get the Planck mass exactly at the geometric means between those two values. And so, yeah, it's like the scaling factor of the universe. We applied it to biology as well.
Excellent.
And I'm publishing this in the next few weeks. I presented it at the conference on consciousness, physics of consciousness. The conference that Roger Penrose and Stuart Ameroff put together every year. And so I presented this paper where we're scaling from the Planck scale up, and we get the carbon atom and the frequency of the carbon atom, and then the water molecules, and then the microtubule and the tubule and the microtubule and then the bundles, and then eventually we arrive at neurons, and we're nailing, using this scaling factor, we're nailing every one of those frequencies all the way into the brain. We start with the Planck frequency like at like crazy, like 10 to the 42, and we end up at like 30 hertz in the brain, scaling like this, and we're kind of nailing every one of them. Is showing that maybe consciousness is actually information feedback from the structure of space at the quantum scale.
Have you looked above the neuron, and have you seen higher scales? Like, for instance, could we see some sort of, obviously different from us, but some sort of consciousness at the planetary scale, like James Lovelock said of Gaia, or the stellar scale, or the galactic, or they talk about a universal mind. Have you looked at actually scaling it further up?
Yeah, we scaled to like planets, stars, galaxies, clusters, superclusters, and yeah, we're nailing all these scales. Yeah,
It's the same.
It's all, yeah, but it's a repeat in some ways of what Carr and Rees did in '79, but with more precision, with more data from since then, and like in their case, they were kind of hanging that in mid space. They didn't have a mechanism why this alpha G is scaling this way, or or Dirac, but here we're tying it to like the structure of the atom itself, the proton, the electron, and so on.
Okay, that is amazing,
Yeah.
Nassim. I just have kind of one final question. Thank you so much for your time. I know it's getting late there.
It's my pleasure.
Basically, in my audience as well, look into the unknown. I'm personally very interested in the nature of reality. That's really why I started this YouTube channel. That's why I'm interested in physics, and why I'm so curious about the phenomenon. But in all your research over many decades into the physics, and I'm sure you've also looked into consciousness, like we just talked about. What do you think it means to be human? What do you think lies for the future of humanity?
Right. I mean,
That's a big question.
It's a deep question.
Yeah.
Yeah.
What is the meaning of life, Nassim?
You kept the easy question for the end, right?
Yeah.
I think what it means to be human is really to learn and expand our capacity to learn, and our empathy for the universe, for everything, for the world, for each other. I think the meaning of life is to like, I feel, I'm just gonna speak from my own experience, but I feel I'm in contact with a fundamental field, and that field is the source of my awareness. That like I'm not my body, I'm that field, and that I'm gathering information through every means I can get. I got this body to like figure out things, and touch things, and understand deeper and deeper level of my existence and my relationship to all things. And I think that like every point in space is doing that in its own way, participating in its own way. And I'm like one of the points, and the other person is one of another point, that's seeing it from a different angle, so it's seeing it a little bit differently than me. And so I feel like this leads to a really profound, like deep relationship with the universe, a deep relationship with like the incredible will works that we're embedded in, that we're participating in, like that we're in this incredible creation that we're part of and that we're participating in. We're not just part of it like as like, oh, the universe made ants and made us and made, but actually if you look at even the evolution of biology, you can see that the structure is getting and more complex and more dependence on all the other, we need the ants, we need the bees, we need we need the trees, we need, all this has to happen for us to be here and to even like contemplate the thoughts of what the heck is this experience I'm having, right? And so, I feel like so much gratitude in some ways and empathy, but so much gratitude for this incredible experience as a result of feeling connected in that way.
Okay. Oh, that's
Yeah.
amazing. Yeah, I can't wait for your peer-reviewed paper to finally come out. And we didn't really touch on it, but and I don't know if you share it publicly. We talked about it before, but your first paper was taken down by Los Alamos, and I can edit this out if you don't release this publicly. But I find that very interesting, and I just think it's a shame that it seems like you've been blacklisted and your work has been ignored for so many decades. And it sounds like that was the beginning.
Yeah, right from the beginning, my paper with Dr. Rauscher was censored off the archives. That's Cornell University. That and where at the time, at least the servers were in Los Alamos. I had friends inside Los Alamos, so I tried to figure out what was going on, why it was, and I was never able to get a clear answer. And so since then, I was blacklisted, and that was in 2004. And so even people that try to put, yeah, I mean, it's been difficult. And then many different ways I was censored, even off Wikipedia, and so I'm not allowed to have a Wikipedia page. That's why you won't find me there. Many ways I've been like blocked from publishing, blocked from giving conferences and physics conference. It's been a long journey, a very long journey. Um,
Why do you think
and
that is? Why do you think you were blocked and blacklisted?
um, I think it's a combination of things. It really is. It's a combination of uh, a certain amount of wanting to keep way of thinking, a certain paradigm of, functioning, for students and so on, that like professors, are teaching in universities and so on. So that's been like the fear of like something completely disruptive, arising. Certainly, I didn't help my case by talking about consciousness very early on, talking about spirituality and all this, which, now is more acceptable in physics. There's so many physicists working on consciousness and all this at this point. It's like, there's so many theories of consciousness out there. It's crazy. But at the time, if you were doing anything with consciousness, it was considered non-rigorous and it didn't belong in physics and so on. And so that didn't help. As well, I was interested in ancient civilization, the fact that there's all kinds of anomalies on our planet in ancient civilization. And I was interested in understanding how is this possible? Like 1,000-ton blocks of granite don't just move across the desert. I don't care how many slaves you got, and so on. And so all this like didn't help like make friends. And I'm kind of shy to talk about this because I'm not a conspiracy theorist at all. I don't like, I always give the benefit of the doubt to people and so on. But there's been a certain amount, and you can see it in the history of physics. There's been a certain amount of censoring of the concept of a fundamental field that like many people have experienced direct um, difficulties in bringing this forward and discussing it openly. You even have interviews. This is an interview in French, so most Americans don't know about it, but it's an interview from Oppenheimer and a famous French physicist. Oppenheimer spoke fluent French, so he's being interviewed in French. And they're talking about the difficulties of secrecy in physics. And, there was some good reasons at certain time to like segregate some information, like how to make an atomic bomb, during the Second World War was a good idea not to like just put, publish papers on this. But, they're talking how it makes stuff difficult and how it makes physics like fragmented. And so the secrecy makes it so that like physicists are not able to communicate appropriately with each other, and makes the field go. And at one point, I think that's really telling, because it just blew my mind when I saw it for the first time. I had to rewind and listen again and rewind and listen again, because you have the French physicist that's talking about this with Oppenheimer, and he at one point he just blurbs out. He goes, "Yeah, they're even censoring stuff about. There's even secrecy about stuff about the gravitational constant."
Huh.
And you can tell, kind of like you can tell from the expression on Oppenheimer's face that he goes, like, don't talk about this.
Wow.
And because I mean, the what is secret about the gravitational constant? I mean, this is Newton, like 16 whatever. Like, what are we like? What is unknown about the gravitational constant? So
Yes.
you see, and this is an interview in 1957, I think, or something like that. So there's been some intent to make this kind of knowledge difficult to obtain. And I would be really lying if I was to say that it hasn't affected me. It has affected me deeply. It's been super difficult. It's been super hard in some ways to like stay true to myself and believe enough and not completely implode from the pressure of all these different angles of difficulties. Yeah, it's been hard. It's been a long journey.
I think my audience actually, or many of my audience, can completely relate. A lot of the people I've interviewed, like the person I interviewed yesterday, Dan, I already mentioned him, have had amazing experiences, where they know without a doubt, there's no way Dan Isbell, test pilot for so many 70 plus different aircraft, doesn't know how to identify a craft, and he had access to all of our top secret technique. He was the test director for the F-22 and the B2 before anyone even knew the B2 was even on anybody's radar. Literally,
You were a test
he knew
pilot
that.
as well, no?
I wasn't. No, I was not. I was just I was an F-16 pilot and then an aggressor. This plane, electronic attack. I focused on electronic attack.
I
Um,
see.
so I wasn't. I did functional check flights. We talked about that, where you would test an aircraft that came out of the depot. Once it was worked on, you would just make
Oh
sure it
yeah,
worked. And
yeah.
he did hundreds of those. But he's just one of many who I've interviewed who have seen something that they argue was completely real. There's no way it wasn't, and yet that information was hidden. And all the people they talked to said they were crazy, to where they would just not tell anybody about it. Even crazier experiences, direct contact with alien beings, etc. And there is a lot of I've heard as well that the one of the reasons that it's being kept hidden is because if there's a reality that these craft can go faster than light, essentially using some sort of electromagnetic or zero point energy, most likely as you're investigating, then it would completely disrupt the whole system. And so the
Mhm.
basic that's why they cannot release any information on the real phenomenon that they're investigating. It is that simple knowledge of this could give amazing power to the adversaries. If they knew that the field
Right.
existed and that if you could access zero point energy, then you could have access to incredible energy. And so you could easily develop a weapon, as humans always seem to do. So that's one of the main reasons that the argument is that they keep it completely secret and hidden. And yeah, will harm and damage people such as yourself or many other along the way.
Yeah, which is really, really sad. I've seen horrible things, you know, and there's no reason to propagate this, but I've seen horrible things and done to people, and I, which, yeah, have left wives and kids behind, and I think that, like, in some ways, um, the truth will always prevail. So
Yes.
it's gonna, I just know the truth will always prevail. And so, like, it's easier to go with the truth. And imagine what humanity would be capable of if we actually use this knowledge for the good of humanity. If we transcended our little territorial disputes and, like, learn to debate. I mean, this when we're having this conversation, there's been horrible things that happened last week, in the world, and people losing their lives, and I just saying, like, why just talk it out? Like, why can't we just talk it out? Like, the only thing that can happen out of talking it out is that we all get new ideas and new sets of information, and grow together, and evolve. And, like, people don't necessarily realize how fragile our existence is, like, we're on a planet flying through space at, like, incredible speed, with a little teeny, like, layer of gas that's keeping us alive, that is just remarkable. It's still there, after all these thousands of years. And to think that it's always going to be there is ridiculous. It's going to go one day, right? It's just not going to stay there forever. And one day, it's going to look like Mars around here. And, this is, so we're all on this endeavor together, and we're all incredible. People are incredible. People are incredible. Like the existence of one human being is an incredible thing. Like I was calculating the number of protons in a human, and like it's more than stars in the observable universe. It's like wow, like the complexity and the amazing miracle of existence, right? You don't have to be religious about it. It's just a fact. It's an amazing thing. And to like to think that like we're all on this little ball flying through space and we can't get along, it's crazy. It's crazy. Like, let's sit down and talk. Come on, we can talk it out, right? And we're in some ways kind of being pulled in certain directions by like publicity and media and all kinds of things that are like showing us extremes, right? But the neighbor is not an extreme. The neighbor is just the neighbor, and he might have a different opinion than you. So but you can talk with your neighbor and still be neighborly, and everything's all good, and still have debates about who you think should be the next president or not, and everybody's okay, and everybody's fine, and everybody's respected and honored for their opinion. It's all good. It's really all good. It really is. um, I I really hope that we can transcend this moment. I think we can. I think we're on our way. I'm very, very uh, positive about where we're going. I think there's still a lot of hurdles to go over, but I think when I look at the world in general, people like, are awakening and the light is in their eyes. And I really think that the physics to back that up are coming out. And there's more and more people catching on, and it's really exciting. It's exciting to see, and I'm just so honored to be part of it. I'm just, even if I can only bring just a little teeny piece, just a little teeny piece to the whole thing, then I'm so grateful for it.
Well, I think you'll most likely, very probably, bring more than a little tiny piece. So I think I really
Thank you.
appreciate all your work, Nassim, and I've learned just a great deal looking through your papers and studying up for this, and watching your other interviews as well. And I've learned an amazing amount here, getting to ask really the specific questions I'm really curious about in my mind, and so I really appreciate it.
Yeah.
Thanks for all your time, man, and I hope to have you on again.
Thank you, and thank you for the great work you're doing, and educating, and your curiosity. I mean, that's amazing. That's the main thing. We got to stay curious, and we got to keep learning.
Exactly, and like you said, I think the truth, there's an infinity amount of solutions that are incorrect, right? But there is really only one truth. I mean, although depending on your perspective, right, you can narrow it down, but there really is only one
Correct.
ultimate truth to the
I agree with
reality.
that.
Maybe it's
Yeah.
blurry at some point, but ultimately there's only one. So
But
yeah, I
yeah,
think we'll
when
get
you
there.
drill down, eventually you should get to one, and it should actually be something sensible that makes sense. That
Yes.
like that is something that you can like saying, well, is this quantum? The quantum world is just weird, and
Yeah.
we can just yeah. I think I find that very unsatisfying, and I think it's generally incorrect. I think whatever is weird in the physics we're writing is usually because we missed something.
Exactly. Yeah, I think
Yeah.
spot on, Nassim. Awesome, man.
Thank you.
Well, thanks again, and have a great rest of your night. Thanks, audience, for watching this far. I hope you enjoyed it as much as I did. I'm sure a few of you did, for sure. Excellent.
We'll
Okay.
have to do it again.
I hope so, Nassim. Yes, without a doubt, man. Thank you. And I hope to meet
You
in
take
person.
care.
I want to go.
Yes. Maybe we'll go surfing.
Exactly. You come to Portugal, we'll go surfing for sure.
Awesome.
Okay. Awesome.
You take care.